It's back. I know that you have a deep love of stoichiometry AP Chem. So I know that you've been missing it now that you can do it with masses and molarities. And now we're going to do it with gases. And I know that it's just going to fill your heart with excitement. So we're going to be getting into gas stoichiometry today. I actually don't think gas stoichiometry is that bad. I think it's easier than stoichiometry with molarity for most students because molarity, we still don't love that. So I think it's a little bit easier and it's not that complicated. So we're going to kind of talk about it. What's the same about stoichiometry, and this is every single time, is your process for solving it. So you first need to make sure you have a balanced equation. Then you have to figure out what you're solving for. And then this is the most critical part. Actually, the what you're solving for is the most critical part. But then you have to get your starting information into moles, always the same. Then you switch from moles of what you're solving from to what you're solving for using your mole ratio. And then you solve for your answer. So that is exactly the same as it always has been. What is different in the case of a stoichiometry with gas laws, though, is the start or the finish of your problem. So instead of ending with a mass or a molarity, you are either going to need to convert 2 moles of a gas that you have to start with, or you're going to solve for moles of a gas and use a gas law to finish the problem. And those two relationships are either going to be the 22.4 liters per mole relationship if the reactions occurring at standard temperature and pressure, or PV equals nRT, our ideal gas law. Now, I have told you before that the 22.4 liters is at a STP. If you forget that, no matter what, the ideal gas law is always going to work. So I guess I always keep that in my back pocket that when all else fails, if I don't recognize that it's at STP, I'm going to use my ideal gas law to solve. And so honestly, there's not much more to this. So we're just going to straight up get into some examples. So I'm going to post the example here. We'll work through it, go through another one, go through another one. And I'm going to try to give you the 3 different scenarios that you're going to see so you can get some practice at that. Okay, so here is our first example. So if you want to give this a try because you feel pretty confident on your own, that's fine. Otherwise, I'll work through this example with you. Example number 1 says zinc metal reacts with hydrochloric acid to produce hydrogen gas and zinc chloride. What mass of zinc is needed to produce 50 milliliters of hydrogen gas at STP? Okay, so first trigger, we have STP here. So if you have a gas reaction happening at standard temperature and pressure, it's going to be so much easier because you don't have to deal with the ideal gas law. You could, if you can't remember. Again, ideal gas law will get you out of all of these problems, but it's going to be a little easier if we don't. So I'm going to work this out, like I said, on the notepad here so that we can kind of work together on this. So the hardest part with these, and places where I see people making errors, is that they don't read the problem carefully and they don't know what they are talking about. So you have to just be very careful. So like I said, make sure our equation is balanced. We've got that. Zinc, it's all balanced for us and taken care of, which is nice. Next thing we want to do is figure out where we are starting and what we are going to. So we read through the background. It's really great narration there. Okay, we're getting to some useful stuff now. What mass of zinc is needed? So I am solving for zinc here, and I am looking for my number of grams of zinc because it's what mass is needed. Okay, so then I have 50 milliliters of hydrogen gas I want to make. And it's at STP. So it's asking me how much of this do I need to make this much stuff. So again, you could use the ideal gas law if you wanted to, but because it's happening at standard temperature and pressure, it makes life a little bit easier. So what I need to do is I need to get this starting information into moles. And like I said, there's always 2 options. There's PV equals nRT for any circumstance, or we can recognize that there are 22.4 liters in every mole, and we can use that in our stoichiometry as well. And that's what I'm going to do in this example. So if I have 50 milliliters of hydrogen, now this is in liters, so we got to make this work. I'm going to just convert 1,000 milliliters for every 1 liter, okay? And I've got to get this into moles. This is my conversion factor to make this happen. This is not grams. This is not molarity. This is gas. So I am going to do 22.4 liters for every 1 mole of this hydrogen gas. And remember, that's for anything. So it could be any gas that we have here. Now I'm in moles. So my first step is always starting info into moles. So now I'm into moles with this step here. Then I'm going to hit it up with my mole ratio, and I'm going to zinc here. So it's a 1-to-1 mole ratio for every 1 mole of H2. I need 1 mole of zinc to make that happen. So again, mole ratio. Okay. And then I need to solve, and it's asking me to go to grams. So anytime I need to solve in stoichiometry for grams, I'm going to use my molar mass, and 1 mole of zinc weighs 65.38 grams from our periodic table. So if I've got my zinc here, now it's just a matter of using some dimensional analysis. So I've got 50 divided by 100 divided by 22.4 times 65.38, and that gives me... I didn't get the answer. Hold on. Let's get the calculator out. Unprepared. What a rookie mistake. Otherwise, this all happens through the magic of television. So I end up getting 0.146 grams of zinc are necessary to make that happen. Okay, so this is just like stoichiometry that we've done in the past, but we've got to get our starting information into moles in a different way. Now, I could reverse this, and I could give you the grams and ask you to solve for how much gas you would make. And in this case, you would just invert the 22.4. Okay, so that is one way that you can do that. All right, let's look at example 2, because we love good examples. Okay. This is going to escalate a little bit here. So example 2 says, what mass of urea is produced from 9 liters of ammonia at a temperature of 23 degrees Celsius and a pressure of 14 atms? And the reaction is 2NH3, CO2 turns into CH4N2O and H2O. Now you look at this and you might be like, I don't know what urea is, but you can figure that out through process of elimination. So you should know that NH3 is ammonia. You should know CO2 is carbon dioxide and water is water. And if you don't know that, I feel like you're in the wrong place. So what's left is going to be urea here. So we're going to give this one a try. If you want to pause the video and try it and then check the answer, you can. Otherwise, if you're looking at this and you're like, lady, I got nothing, then you can follow along with this example as well. Kind of flipping back here and forth. So, okay. So here's example 2. Urea, we're going to produce from 9 liters of ammonia at a temperature, blah, blah, blah. Okay. So if we check it out, remember, first thing always is to have a balanced equation. We got 2N, 2N. We have 6 hydrogen and 6 hydrogen, 1 carbon. Hold on here 1 sec. That is unbalanced, and that's not great. Mrs. Audemire looks silly now. So let's check this out. Oh, I lied. It's CH4. Haha, then copy it down. Your girl here is struggling today, guys. So CH4N2O, I was going to say. That does not look right. So CH4, there we go. And then our oxygens are good to go. Crisis averted. So if we look at this, it says what mass of urea. So this is the urea here. I do not know how many grams I am going to make, but it tells me that I have 9 liters of ammonia. So I've got 9 liters of this stuff. I know my temperature is 23 degrees Celsius, and I know my pressure. So I've got a lot of information for urea here, which means that I could probably do some work. So in my dimensional analysis and my stoichiometry process, I'm going to go from ammonia to urea. Now, this starting information, I need to get into moles. And I've got a volume, a temperature, and a pressure, which means I can get my number of moles. So if you think about PV equals nRT getting me my number of moles here, since I'm not at standard temperature and pressure, that's what I'm going to have to use. So I'm going to be solving for my N in this case. So I got to get N by itself. So I'm going to have N equaling PV over RT. This is a time-consuming process. I will give you that. So usually what you'll see in a college board problem is they'll ask you to find the moles of gas in one part of the problem, and then in the second one, they'll ask you to use these moles of gas and then turn it into your answer. That can be tricky because people want to turn their starting information into moles, and then they're like, but I don't know what to do. So watch for that. So I'm going to get this into my moles. I have 14 atmospheres, 9 liters, okay, divided by my R, which is 0.0821 atmosphere, liter over mole, Kelvin. Watch your pressure to make sure that they are in atmospheres. Watch your liters to make sure they're in liters. And then remember your temp has to go into Kelvin. So this is 23 degrees Celsius. And so in your Kelvin temperature, that's 296 Kelvin. And so when I plug all this in, my units cancel out, and that's great. And then my number of moles that I have is 5.18 moles of my ammonia. Okay, so I've got 5.18 moles of NH3. And now I've got starting information. So now I can finally start my stoichiometry. You could continue off of here, but I'm going to run out of paper, so I'm just going to restart it over here. So I've got 5.18 moles of NH3. And I know it seems weird to start your stoichiometry that way because we're so used to starting it with grams, but you've just got to get used to that. Okay? So that's my starting information into moles, all of this jazz. Now it's mole ratio time. So it's 2 moles of ammonia for 1 mole of urea, the stuff I cannot write down correctly. Okay? Now, if we look here, I'm going to grams. So if I'm ending in grams, that means I can use my molar mass. So I'm going to figure out how much 1 mole of that weighs. Okay. And if I do that, I add all that stuff up, and I got 60.062 grams. And I do believe I actually did do this one, and the answer comes out to be 155.56 grams when you put that into your calculator. So if I have this much, 9 liters of gas at 14 atmospheres of pressure in this temperature, I should be able to produce 155.56 grams of urea. Seems like it's not that much, but honestly, 14 atmospheres is a pretty high pressure. So, all right. Last one. Hopefully you are feeling a little bit better about this. I feel like this one is one you should definitely be able to attempt on your own, and then just check your answer. So example 3 says potassium metal reacts explosively with water by producing hydrogen gas and leaving potassium hydroxide in solution. What volume of hydrogen gas is produced when a 0.50 gram piece of potassium is added to water at 26.5 degrees Celsius and 1.014 atms worth of pressure? And then it gives you the equation. So if I were you, I would pause, write down all this information, see if you can figure out how to solve it, and then come on back and check. All right, here we go. Last one. These all have tons of words, which makes them somewhat more difficult too. So let me get this full screen. Potassium metal. Good story as we read through. Okay, the meat of the problem. What volume of hydrogen gas is produced? So I am looking for hydrogen gas here, and I am looking for a volume. So I'm probably going to be doing like liters. If it's not specific, I would solve for liters. Okay, produced when 0.5 grams of potassium. So we've got that. Added to water at 26.5 degrees Celsius and this atmosphere. So you say to yourself, you're adding it to water, that makes sense, but why do I care about these temperatures? Because I'm talking about the water. Well, if the area around the water has this temperature and this pressure, that's going to help me figure out the conditions for my gas. So it's 26.5 degrees Celsius here, and it is 1.014 atmospheres worth of pressure. So last time when we did this, we were able to start with moles. So you look at this and you're like, I got numbers here and I got numbers here, but I'm solving for this one, looking for liters, right? So in theory, I'm probably going to have to use PV equals nRT, but I don't have the volume, and I don't have the N, okay? So my problem, I'm solving eventually for liters, but the problem is I can't get to my liters until I have my number of moles, and that's what the stoichiometry is going to lead us to in this case. So I have 0.50 grams of potassium, and I got to get that into moles, and that is just using the molar mass like we are so familiar with. I have 1 mole of potassium, and that weighs 39.10 grams, right? Grams cancel out, and we're in moles of potassium. So our starting information is into moles. Then I go to the mole ratio, and I'm solving for hydrogen. So it's 2 moles of potassium for every 1 mole of H2. And so if I go through and solve, I get 0.00639 moles of H2. Now, I know for some of you, your inclination would be to drop off some of these numbers here, but we do not want to do that because we have at least 2 significant figures here. We don't want to lose them. So I'm going to keep these numbers until we get to the end. Okay. So then we've got our moles here of our stuff. Now we can get to our liters in this case. So we've got PV equals nRT. We are solving for V this time, so volume is equal to nRT over P. And I'm going to put all my stuff in. So I know I've got 0.00639 moles of H2, okay, times my R value. Again, watch your units here. Oops, as I do them wrong. Oy vey. Okay, so 26.5 degrees Celsius in Kelvin is going to be 299.5 Kelvin. And then my pressure was 1.014 atmospheres. Units of moles cancel, atmospheres cancel, Kelvin cancel, and we are left in liters. If I put this all into my calculator, I get a volume of 0.155 liters. And so if I want to do the rounding now, I would go to 0.16. I don't want to lose that number here because when these disappear, they start to kind of throw off everything else before it's time to throw them off. So we want to keep some of these numbers here. Now, I guess a word of caution. Places where I see people making mistakes in these situations is what they'll do is in a problem like this, they will not go and do the mole ratio. They will just figure out how many moles of the potassium we have. That's in grams, and it's asking us for H2. So you need to be very careful when you read these that you are actually doing what it's asking for. If this was talking about potassium and you were turning the potassium into a gas and then you wanted to figure out what the volume was, totally a different story. But since we're switching to a different chemical, you need to make sure that you have the right chemical, and then you have the stoichiometry and the mole ratio in there. Okay, so with that, you're going to want to try some problems. We are going to be having a lab on this where you're going to be having to do some stoichiometry and doing some figuring to figure out how much of a gas you're going to produce. So if you have any questions, please make sure you get those things cleared up. Otherwise, you know what I'm going to say. Good luck.